Swayam Prabha. Digital India. Educated India.
I'm going to speak about the fluid dynamics of diabatic flows. This is a very classical, let's say, okay? And why it's important to study, for example, this topic. Of course, the application of fluid mechanics are immense, okay? But since this is a course in multi-phase heat transfer, of course, we need to think about convection, okay? Yesterday, we had a lesson about conduction mainly. Okay, with the different parameters, heat capacity, thermal conductivity, diffusivity, and so on. But as you know, as I said from the very beginning, there is also the second way of transfer energy, which is the convection. The convection means that we have the transfer of energy between a surface, a solid surface, and a fluid that is moving, gas, liquid, whatever. Okay, so this means that we have the transfer of heating at the molecular level due to the transfer of kinetic energy, but in this case, due to a difference of pressure, we have also the movement of the liquid, of the gas. So together, so there are in fact two contributions. The things are becoming very complex, okay? Of course, when we are looking at the fluid mechanics, we have to write a conservation equation, like the equation of heat. The equation of heat is nothing else than the balance of energy entering in a volume or going out or being generated inside the volume. And here we need to understand how it's possible to write the equation of motion when we have, let's say, to consider the balance of, again, mass, momentum, and energy. So how is the form of this equation? Okay. So, why is complex? Because we have a really different phenomena, because the two, let's say, processes of molecular exchange of energy and the motion of the fluid makes the things complicated in the sense that we may have different forces acting on the system. For example, we may have pressure, so we have a force convection that is moving the fluid. Okay, and so we have, let's say, the transfer of energy because of that, and we are calling force convection. But maybe we don't have, let's say, an external pumping system or a compressor or something, but we have the motion of the fluid because we have a difference of density inside. And the difference in density is very clearly coming from the fact that we have a gradient of temperature. So we have a gradient of temperature. This means that we have a gradient of the density. Then we have a buoyancy force. And the buoyancy force is putting the fluid in movement, creating again a movement of the fluid in the convection. And we are calling this natural convection. So already there is a big separation of the things. So in order to deal with this very complex situation, we can use the Newton's law of convection, which is in fact a simple law, but all the difficulties and complexities are inside the H. So the trick is to know how much is the H, also for the multi-phase flows. The rest is obvious, almost obvious now. Of course, not at the time of Newton, but now, yes. No? Okay. So if we have a difference of temperature and we have a surface, the power that we can transfer is about, it should be proportional to the difference of temperature. It's obvious, no? The area that is covered, how proportional? Oh, we don't know. We put an H. We put a coefficient of proportionality that is fine. The problem is that we need to understand how much is H, which is really not obvious. H is not the property of the fluid, like a conductivity, for the solid, the fluid, and the gas. Now, this is something else. Depends on many, many characteristics. So we are studying with mono, we are studying sprays, impact, to cool a surface, for example, and then we have an H that is depending. We need to understand that, but for many parameters, so the dimension of the droplets, the velocity they are impacting, with which are they impacting on the surface, so the natural fluid motion, let's say. The surface geometry, how the surface is done and so on. The roughness, for example, the contact angle, the wettability of the surface. The properties of the fluids. Yes, why not? I mean, for example, all the property as we saw yesterday are also very important. If it's a conjugated transfer means that we need to take into account solid and fluid. If we have a droplet impacting on the surface, the droplet is able to cool down the surface, right? So then we have a different exchange of energy in time during the droplet impact. Okay, so there are really a lot of parameters. Another point, and I will be not able in 1 hour to speak about that, but I think that this audience should know it, that we have also different kind of motions. And a very naive way to represent the different kind of motions is of course related to the fact that we may have laminar flow and turbulence flow. In the laminar flow, the streamlines are always very nice, smooth, they are going all together, okay? When we have a turbulent motion, we are going to measure in one point and we have a chaotic situation. Okay, so we are measuring one point, and in time we have an oscillation, we have a chaotic conditions, and it is very, let's say, it's not easy to have a prediction of what is happening afterwards. In fact, it's not possible to predict at a very short time. We need to wait a little bit of time to average the motion and to understand what could happen even in terms of fluctuations, the intensity of fluctuations, and average the value of the velocities. So the treatment of what we are doing now is mainly is coming from this book. Is one of my first reading in this topic, which is really an excellent introduction in the heat transfer, fluid mechanics, multi-phase flows, multi-component flows, and so on. It's a very famous one, Bird, Stewart, and Lightfoot. So, how can we deal with this matter? Like we have done for the heat equation, just in the same way, we can consider, let's say, a volume, a small volume, okay, with a different orientation. Can be, let's say, a cube, so that is simple, okay. We dimension the x, the epsilon, and the y and the z. Sorry, the x, the y, and the z. Okay, so. Of course, what we can try to understand is that we are doing the balance of mass, momentum, and energy inside this volume. Okay, so the first balance is of course the mass continuity. So is the balance of the mass, and so inside the volume, the rate of increase of the mass must be equal to the mass that is coming in minus the mass that is going out. Obvious, okay? Now we need to translate this sentence in mathematics. How can we do it? Well, we can consider that we have the density multiplied by the velocity. So it's a volumetric flow that is going inside, the mass flow that is going inside in the direction of x, and is going inside through the surface, the x, the y, the y, the z, the y, the z, okay? On the other side, we have the opposite, but it's with a different sign. So one is entering, the other one is going out, okay? And which is the increase of the mass inside. Well, it's linked, for example, to the variation of the density inside the volume. Okay, so it's the volume is fixed in this case. Is that the x, the y, the z. So we are going to have the x, the y, the z, the rho, the t. Notice that we are now starting with the partial derivatives, and we are going to have partial derivatives everywhere until midday, until noon. Okay, so will be like that. So if you are doing this calculation and doing the first time, then I'm not doing anymore, but only to introduce you. It's quite, let's say, straightforward because we have this equation of balance. So we translate my words before in a mathematical way. So at the end, we are landing with this expression. And this expression is saying that the variation of the density in time is equal to minus these derivatives with the three coordinates, x, y, and z, of what? Of the mass flow rate, so rho Vx and so on, okay? The specific mass flow rate, because we don't have the area, because I multiply by the area and then I divide everything by the volume. So at the end, using a vector notation, we have that the partial derivative of rho with respect to t is equal to minus, and then we have a gradient of rho v, okay? This is the net rate of mass addition per unit volume by convection, okay? So the convection of the mass. This is, I think, is it fine for you? Everybody, you know, it's a very classical, okay, way. Okay. Now we need to introduce the momentum. And we need to consider the viscosity. The viscosity is a very important point because when we have, let's say, a flow on a surface, the velocity at the surface is considered, let's say, 99% of the case, zero, no, the same velocity of the solid. So if the solid is fixed, will be zero, okay? So this is interesting, but it poses a problem because then the flow is moving. So somewhere there is a change from the main velocity to zero, because here is something and there is zero. So what's happening? And okay, we have in fact a profile. We have a velocity profile of the motion when we are in presence of a wall. And the fact that we have a profile means that the velocity is changing in the direction normal to the wall. And this is creating friction. Because if, for example, we are considering something very, very viscous, you can understand that if I want to push, I need to do some work. Okay, otherwise nothing is moving, right? And this is really the force that we need to have for each of the layers of the fluid in order to put the fluid in motion. Okay? Something that we know, we have this law that is saying that this force is proportional to the gradient of the velocity. Okay? And we can write in this way, we can say that the force tau ij, which is the force in the direction of j that is linked to the gradient on the direction e, I said e or I. Tau ij, is equal to minus the viscosity, the dynamic viscosity, multiplied by the partial derivative of the velocity in the j direction over the direction I, or the direction where the velocity is changing. Okay? This is a very classical notation. Okay? And so this is a very important equation that is giving us the shear stress that we have in this motion. Now, which is the other force? Of course, is related to a pressure. Okay, so the pressure and viscous forces are acting on the planes that is in the fluid perpendicular to the three coordinates, and you have here the case A, B, and C. Okay, so the pressure force is always perpendicular. So, for example, here we have P delta x. Well, delta is saying that we have only this direction. Okay, we are going to see that afterwards. Okay, so the force will be in this direction. Here will be in that direction, will be y, and then we have the force in this direction will be z. Okay, so the pressure force instead of the shear stresses are always present. Even if there is no motion. This is so-called hydrostatic pressure. Again, it's something that you should know. I'm going fast, okay? It's important. So the viscous force, we said that we are entering in this game when we have a motion, okay? The point is that the shear forces, in general, they don't have a specific direction like the pressure that was normal to the surface. They may have them going in different direction because the motion can be in different direction, okay? Okay? The motion of the fluid inside this volume can have a Vx, Vy, and Vz components, so it can be everywhere in all the possible directions, Okay? So this means that, for example, we can think to a component of tau in the, let's say, that is linked to the plane in x direction, but this component tau is depending on the components of velocity, all three of them. Okay? The same thing for the y, the plane on the y, and the plane on the z. Okay? So each of the three forces as components, which are scalars. Okay? So tau x is in fact as components tau xx, tau xy, and tau xz. Okay? The things are starting to become a little bit more complex then. Okay? In fact, we can write this in terms of a kind of tensor, saying that pi ij is equal to p delta ij, and now it's clear that p delta ij is nothing else than the Kronecker delta, which is in fact 1 when I is equal j, and is 0 when I is different from j, plus tau ij. So this is becoming our tensor. And this can have two interpretations. One, pi ij is the force in the j direction on a unit area perpendicular to the I direction, where it's understood that the fluid in the region of lesser xi, so smaller xi, is exerting the force of the fluid on greater xi, because the viscosity, pay attention, is opposing the motion. In fact, there was a minus, I forgot to say, because it's opposing, the force is going against the motion. So when you have a very high viscous fluid, is opposing to the force, so in the direction of the motion. And then another way to say is that pi ij is nothing else than the flux of the j momentum in the positive I direction. Okay. The things are very clear, I think. The problem is that we are landing with a matrix. So we are landing with a tensor that has in the three direction, and we have also the three components. Okay? And as you can see, because of the delta Kronecker, we have that in the diagonal of the matrix, we have also the pressure. And one other point is that the pressure is the same. We don't have Px, Py, and Pz. This is another very important point. We have one pressure for the system. Okay? This is an important thing to say. Now, tau is going to be then the viscous stress tensor with the component tau ij, and pi is the molecular stress tensor, it's so-called molecular stress tensor, with the component pi ij. So, the viscous stresses then can be a linear combination of all the velocity gradients. So we can write tau ij in this form, as we saw from the matrix before. The point is that since we have three directions, three components, and so on, what is happening that we are going to have 81 components. 81. So the things are becoming very complex then. 81 components to consider. And they are called velocity coefficients. Okay. So we can try to simplify the 81 components. Consider that I'm now treating the case of Newtonian fluid, okay? But in principle, there are fluids, non-Newtonian fluids, where we cannot say that we can simplify so easily the matrix. So we need to consider, let's say, also the interplay of stresses in the different directions. Especially for example, non-Newtonian, non-isotropic fluid is a big mess. I need to surrender. I'm not a specialist in that. It's becoming really very complex because it's very difficult to simplify the 81 components there. Okay? Okay. So what is happening here that there is, if the fluid, let's say, in a pure rotation, so it's in rotational, we can have that the viscous force are not present if it's only a rotation. So I'm not entering the details, sorry, but otherwise it's a lesson fluid mechanics of for the master, so it's becoming really too long for that. So believe me, or let's say look in the book, so we have a little bit of demonstration. We are going to simplify the matrix, okay? So we are finding that there are, let's say, symmetric combination, and this is helping a lot, because this means that many terms are going away, okay? Or they are the same. Okay. So at the end, when the fluid is isotropic, all the components are reduced, and then we are landing with this expression, which is quite important, that is saying that shear stresses are, let's say, equal a number or a value, multiplied by dvj dxi plus dvi dxj plus b multiplied by the gradient of the velocity, and multiplied by delta ij. So we reduce the number of viscosity coefficient from 81 to 2, which is a good bargain. It's not too bad. The problem is now is to understand what is A and what is B. Now it's very clear to notice that for an elementary flow, this tau yx, for example, must be A dv y. So this means that since for an elementary flow, this equation should work. It's not because otherwise there is no generality, it's not general. It's going to be that A is very simply minus mu, so minus the dynamic viscosity. Again, you are going to have the PDF. Maybe you can think about that, but I think that in this audience, everybody should know this matter. A little bit more complex is the part linked to the B, okay? I wrote, by common agreement among most fluid dynamicists, and the sentence is already saying something about the fact that, well, it can be like that. Maybe someone is raising hands. Yeah, are you sure? Okay, I don't know exactly. Okay, usually what we are using is that B is equal to third the dynamic viscosity minus something, K, and that is called dilatational viscosity, and is used for compressible fluids. So that when the fluid is compressible, we are thinking that is a resistance to compression and dilatation. Okay, this is just that. So mu is due to the stresses in this direction. The other one is due to the fact that when we are trying to, let's say, to have an expansion or a compression, there is a force that is opposing this motion, is opposing this force. Okay, so this is called dilatational viscosity. Okay. So the dilatational viscosity is very interesting. Again, I don't have time to enter, let's say, in this field. There is a theory, the kinetic theory, that is giving a justification for this value. And let's say for a specific flow, we don't have really the value of K. So K is not really relevant. But for real world, and non-ideal fluids and so on, there is a value for K, so we should pay attention. So at the end, if you consider now the viscous stresses in the vectorial form, we landed with this equation, okay? And we can use the vectors, and you can write the same equation with vectors. Consider also that for incompressible fluids, we have that nabla dot V is equal 0. So this part for incompressible fluids is going away. Also it's simplifying a lot, right? So it's not too bad. So this means that these are the viscous stresses for, in the very general form, also with compressible fluids. Again, in 1 hour I cannot enter in the details. There is a course in fluid mechanics by us. So there's 60 hours on that. So I think that to arrive at this point, maybe it's already 5 or 6 hours. So sorry for that. Okay. Then we need to write the balance again. So we need to come back. We studied the forces, but now we need to look at the momentum and the balance of the momentum. Okay. But we know that the momentum is nothing else than rho VV. So this is the fact that we have a mass flow that can be multiplied by the velocity in order that at the end we have a momentum, and we can understand what is happening in the different direction. Again, in the plane x, y, and z, all these momenta have three components because, again, the motion is not predictive. So it's not in one direction only. We have possible directions. So all the terms of an x, y, and z plane, they have three components. So in fact, we are going to land not in 81, but in 9 components. Okay? So these are the components of the momentum, let's say, flux in the 3 directions. It's not too bad, okay, with respect to the 81 components that we had. And we can combine this using the molecular stress tensor, pi, plus now the momentum linked to the velocity, and we have now phi, which is indeed quite useful now, because we can do the same that we have done for the mass for the momentum. So again, with our nice volume, we can say that the rate of increase of momentum inside the volume is equal to the rate of momentum inside minus the rate of the momentum out, plus eventually the forces, external forces that can act on the volume. Okay? So now the momentum for us is phi. Kind of small reminder, phi is what? Is P delta plus tau plus rho VV. Okay? So let's say in the vectorial form. Okay. So I need to skip this, but let's say that we are going to do this kind of operation as we have done for the mass. We are doing that for the phi. Before was the mass, now phi. Okay? In principle, it's the same. We are going to have a phi in x and a phi in x plus the x, or delta x. And then we can say the delta, if you are not using the x from the very beginning, someone is doing that, perfectly fine. We can live with the delta, and then we can say the delta is tends to 0, right? So it's the same at the end. So, and we can have forces. For example, we can have gravity. Gravity will be not the only one. The g can be the gravity, and the gravity has a component because we don't know how the volume is positioned, let's say, with respect to the gravity. It can be in all the position, but can be also a centrifugal force. So if the volume is inside, let's say, something that is moving with a given centrifugal force, can be the acceleration. So the g is a bulk acceleration, in fact, in general. Okay? Okay, but let's think that is a gravitational force, not to make the things too complex and so on. So at the end, we are landing with something that is very similar to the mass conservation, because the mass conservation was this one with the mass. Now we have the same equation with the phi. Okay? And the phi again is P delta plus tau plus rho VV. Fine. This is for the x direction. We can have here the 3 directions. So at the end, using the notation, the vector tensor notation, we are going to have this equation, which is very famous and important, that is really saying what is happening in terms of balance of momenta inside the volume. So this is the balance of the momenta that we can use to establish which is the direction of the motion. So we have the conservation of momentum. And this is expressing the rate of increase of the momentum per unit volume in terms of the rate of momentum addition by convection, as we have seen before, because we have a mass with a given velocity that is entering inside. Then we have the momentum addition linked to the molecular transport, which makes 2 terms. One is the pressure, because if we are thinking in terms of the molecular level, the pressure is nothing else that the sum of the forces produced by the impact of molecules on the walls, okay, or among the others, say, if you have, for example, stratification to fluids. And of course, we have the viscous forces, the viscous shear stresses, plus eventually an external force. The external force here is only G. Again, if we have a ferrofluid, a liquid, and so on, the external force can be something also completely different. It can be an electrostatic force, electromagnetic force. So any force that is acting to the bulk of the fluid. Okay, if the fluid contains, for example, particles that are magnetic, nanoparticles, magnetic nanoparticles, and we are putting the fluid in a field, this is for us, it will be for us, an external force. There are a lot of papers dealing with different fluids like that and so on. So, at the end, we can continue and we can write a different conservation. Also, we can think to the kinetic energy conservation, the angular momentum conservation. These are really the classical conservation laws in physics. The classical conservation laws in physics. It's important to say that instead of writing the partial derivative in time of rho v, for example, for any quantity, we can write a total time derivative. Okay? So instead of writing the partial derivative of a quantity with respect to the time plus v multiply the gradient of c, what we can do is write in this part in terms of the total time derivatives, because in this case the form is even nicer using these total time derivatives. And this is coming from, let's say, the fact that this total time derivative is a way to represent what is happening when we are following the volume. Okay? Again, I'm not entering the details. You can look in the book, or you can look this afternoon in front of the PDF let's say, you can Google and so on. Now I don't have time. So, for a constant rho and mu, because so we don't have a non-Newtonian, we have Newtonian fluid, so mu is constant. We have an incompressible fluid, so rho is constant. Then we can have an expression that is very famous because it's the Navier-Stokes equation. We can have also a Navier-Stokes equation for compressible fluid. Let's stay for a moment on this equation, okay? And if the acceleration terms, so the v over the t, are negligible, are very small, we can write this equation in this form, that is the so-called Stokes flow or creeping flow equation, okay? Which is very important, for example, for studying the particle motions and, let's say, lubrication condition and so on. Or, let's say, when viscous forces are neglected, so this term is gone away, we can write this equation as a simplified equation for inviscid fluid, that is the so-called Euler equation for inviscid fluid. Finally, we have the conservation of energy. Again, the same idea. Now the things are becoming interesting because they are linked more to the Q and W, no? As we saw yesterday. Again, we can express the conservation of energy in words and saying that the rate of increase of kinetic and internal energy, see that we have now kinetic and internal energy, is equal to the net rate of kinetic and internal energy addition by convective transport, the net rate of heat addition by molecular transport, conduction. Then we have rate of work done on system by molecular mechanism, so viscosity and pressure, plus the rate of work done on the system by external forces, accelerations. So we can write down this sentence. I'm not repeating the demonstration. It's very similar to what we have done until now. Only that now we have u plus 1/2 of v squared to transport instead of a phi. But at the end, let's say, the demonstration is very, very similar. And we have this expression that is saying the rate of increase of energy is becoming 1/2 rho v squared. This is the kinetic energy, plus rho u is the internal energy. And the other side, we have this rate of energy addition. In fact, with this term is multiplied by v, because it's going in one direction or the other with a given velocity. Then we have the rate of energy addition. Imagine now Q is a vector. Q is a vector, it's going in one direction. So the heat flux has directions, has components. Then we have the rate of work done on the fluid. And this is, let's say, of course, you have seen that in the basic courses because this is linked to the work that is V delta P, for example, of pump, compressors, and so on. So we have a shaft work, okay? We have shaft work. And then we have the rate of work done on fluid per unit volume, can be by viscous forces. And now you can understand why I use the work as a dissipation work. See, that now is entering inside. Because again, this is the work linked to the dissipation forces. This is the reason why if I'm using the expression of the work with the three terms, the work for the formation, work for the field, coming from the field, and work for dissipation is very nice because then we can connect easily with respect to this equation. And then finally we have the work coming from, let's say, external forces. All these values are vectors. So Q is a vector, V of course is a vector, tau is a tensor, and V is a vector. It's also convenient, for example, to use instead of the internal energy, the enthalpy. I think that you have done this because when you write the Bernoulli equation, we are writing and then you are extending the Bernoulli equation to the energy, so to the enthalpy variation, you are writing with the enthalpy, you are not writing with the U, and you are landing with the, say, the expression, okay, but you know, H plus 1/2 V squared plus GZ and so on. So you are landing with this equation. We are doing the same here. We are using the enthalpy. And in fact, we are going to write this expression using that the internal energy is H minus P divided by rho in this form. Look that we can also, using the, when we have Newtonian fluids, we can rewrite the expression considering also the variation of enthalpy with the pressure, as I said yesterday. So in fact, if you're considering that, you're landing to this expression, which is quite interesting, because it's saying that the total derivative of H multiplied by rho is equal to the total derivative of the temperature with respect to the time multiplied by rho Cp. Rho Cp is becoming very clearly a thermal inertia, plus a term that is linked to the total derivative of the pressure variation, the P over the T, multiplied by this strange term, that is the logarithmus of rho on the logarithmus of T, with the temperature, at a constant pressure. This is interesting because at the end we are going to have this form, and this is a beautiful way to write the energy equation. I found that this is really a beautiful form for the energy equation. And then we can have different situations. For example, when we are considering the Fourier postulate, of course, this, let's say, nabla dot q minus, nabla dot q is becoming the Laplacian of the temperature. It's a divergence of the gradient. So divergence of the gradient, and if the constant is, we have a constant thermal conductivity, this term is becoming nothing else than K multiplied by the Laplacian of temperature. And when the Newton law is used, we can express this term with the two forms, because we can, in fact, let's say, have the part that is linked to the dilatational viscosity and the part that is linked to the dynamic viscosity. If we are putting everything together, we can collect the viscosity on the left and the viscosity on the right and the dilatational viscosity on this on the term of the right. Of course, we are considering a compressible fluid here because the divergence of velocity is still a number, it's not zero. Okay, and so we can write this term with the shear stresses in this nice form, mu plus k and mu phi v plus k psi v, where phi v now is representing the contribution of the shear deformation due to the viscous dissipation, and the other one is the volumetric deformation. And we have different forms, like when we have an ideal gas, this logarithmus rho, logarithmus theta is going to be -1, you can prove it, and then we have this form for an ideal gas. So the energy equation, when we have a Newtonian fluid, ideal gas is of course Newtonian, so in this case it's very simple. When a fluid is flowing with a constant pressure, there is no variation of the total pressure, then you are landing on this equation. You can already recognize that is something that is familiar here. When we have a fluid with a constant density, also this term is 0. And when we have a solid, so we have a stationary solid, we are landing on this equation, okay, which is in fact the heat equation, so the Fourier equation. So we are landing to the equation that we saw for conduction only. So this means that we have only conduction, and in fact is working very good. Only to say that it's very consistent. Everything is very consistent. So we can find also the other equations in this way. Okay, this was very fast. Again, this is usually done in many hours, but I think that for this audience, I mean, it was a kind of a rehearsal, or let's say, resume of what you have already seen. But I think that it was important to pose the basis, because then I will going to use this in the next couple of hours. Coming back to the heat transfer coefficient, for example, if we have this condition on a wing profile, it's very clear that the heat flux is changing along the profile. Okay? So this means that in fact H doesn't have a unique value all over the profile, but is changing in space. So in fact, the total heat transfer is linked to the fact that we need to know the variation of H along the surface. So at the end, very often we are using an average heat transfer coefficient when H is varying. Pay attention that H can vary also because we have an entry, the fluid is entering in a pipe, so we have an entrance length. Or for example, it's flowing above a surface. And also in this case, H is changing in space. H is changing in the direction of X. So also in this case, we are going to try to simulate what is happening using an average H. We said something about the shear stresses, and we said something about viscosity. And I already said that we are building, when we have a fluid in contact, in motion, and in contact with the surface, a boundary layer. But in fact, when you are considering also the heat transfer, we are going to have two boundary layers. One is the viscous boundary layer, and the other one is the thermal boundary layer. So the viscous boundary layer is defined as the position in space, let's say, normal to a surface. The surface can be everywhere in all the positions. We are going normal to the surface, and we are capturing the point where the velocity is 99% the velocity undisturbed. So the one that came, say, from a direction, and the velocity was changed because in contact with the wall, the velocity is becoming 0. So then there is a change. So there is a propagation of this effect due to the viscosity. But at the given point, we can say, well, it's 90% of the undisturbed velocity. This is the point that we fix where we say we have the boundary condition. And so we can reconstruct all the points where we have the velocity at 99% of the undisturbed velocity. And at the end, we have the kind of curve on a profile, on a surface, that is saying how thick is the boundary layer. What is inside the boundary layer? Inside the boundary layer, we cannot neglect the viscous forces. So this means that inside the boundary layer, we have a change of the velocity due to the fact that we are already feeling the presence of the wall. Okay? Above the boundary layer, we can neglect the presence of the wall. But under the boundary layer, we need to think that there is a wall and the velocity will change. So from the shear stresses, we can also build, let's say, simplified coefficients like the local friction coefficient, which is nothing else than the stresses divided by the kinetic energy. For the thermal boundary layer is something similar. If the wall has a different temperature with respect to the fluid, what is happening is that there is a region where we cannot neglect the presence of the wall. So where we cannot say that the temperature is the same that we have far from the wall. And again, we are going to measure now not the velocity but the temperature, and we are going to get the point where we have 99% of the difference of the temperature between the wall and the fluid. Okay? So again, we can reconstruct these points, okay? And we can build, let's say, a curve that is containing the thermally boundary layer. This means that under this curve, we cannot neglect the presence of the wall that has a different temperature, okay? And in this case, instead of the equation for the shear stresses, tau equals minus the viscosity, the dynamic viscosity multiplied by the derivative of the velocity in space, we have here the heat flux, and so we can write an expression that is defining finally what we have in the Newton law. In the Newton law, we have this H, but nobody knows exactly what it is. Now we have a little bit more information. H is becoming minus kf dt over the y, where at the wall, divided by the difference of temperature between the wall and the flow far from the wall. So that is not feeling the energy transfer from the wall if the wall is hotter with respect to the fluid. So again, I'm really resuming very fast, but I think that you understood. It's also interesting that you see that we have here in this expression we have always fluxes. So we have a component like that, and then we have a coefficient, and then we have a gradient of something. So this is typical in physics, no? This can be the stresses, the shear stresses, now it is the flux. Then we have also this form. So there is something that is defining the flux as a gradient of another quantity, okay, in this form. And the form is linked to the equilibrium, okay? When we are not in a thermodynamic equilibrium, this is not the right equation, okay? But usually we can say that all the fluxes in physics are proportional to the gradient of another quantity, okay? This is what is happening here. Inside the boundary layer, we may have what we saw before. So we may have laminar condition or turbulent condition. And the fact that the flow is laminar or turbulent is, of course, has an effect on the value of the H. And now it's very clear because when you have the laminar or turbulent condition, you're going to have different velocity profile. So the gradients are completely different. Okay, so this means that the H is the temperature, the mixing of the layers is completely different. So the H is going to be completely different. And luckily, we have a very strong way to try to understand the effect of the laminar and turbulent flow using a dimensionless number, which is very famous, is the Reynolds number. The Reynolds number is the ratio between the kinetic energy and the viscous work, okay? So, or if you want, you can speak in terms of energy, or you can speak in terms of force. It's just the same, okay? So we can say kinetic energy divided by the work, viscous work, or you can say the inertia divided by the viscous dissipation, okay? Okay, so there are criterion. Why is so important the Reynolds number? Because there are criteria saying that above a given Reynolds, the inertia is dominating. So the viscosity is somehow less important. So the viscosity is not able to dissipate the energy at the various scales. We are entering now in the domain of turbulent fluid mechanics, which is again another course. So I cannot do it, okay? But let's think about turbulence. Maybe I can say something later on. But no, I will say something now. Sorry, I forgot I put this now, okay? So turbulence is very complex. Who was Einstein that was saying that maybe we are going to solve the mystery of the universe, but nobody will know anything about turbulence at the end. Well, we know something more now after 100 years of research, especially looking at, let's say, also studies that are in the mesoscale and so on. What is happening really at the molecular level, because in fact, why it's so complex? Because turbulence is a chaotic motion and is linked to something that is happening at a very, very small scales, okay? So then it's becoming complex. And of course, being a stochastic motion, we need to live with the fact that we cannot predict exactly what is happening in the next second in a turbulent flow. And also not in the next second, even closer. It's a question of space and time, not only of time. So, but we make very good averages. So we can have the idea of the velocity average, we can have an idea of the intensity of the turbulence and so on. What is happening at the nanoscale, at the mesoscale, is that the fact that we have these molecules interacting is producing starting, instead of nuclei, here we have starting vortices at this, okay? And this is in fact the origin of the turbulence at the mesoscale. This will be very interesting. I can give a lecture about that, 2 hours, it's not a problem. Now I need to stop. What is important is that we can characterize in a very convenient way the turbulence looking at, considering the so-called Kolmogorov length and time scales, okay? So if you consider the kinematic viscosity nu, and the rate of dissipation, so the viscous dissipation per unit mass of the fluid, we can write that the Kolmogorov length is equal to the kinematic viscosity powers to 3 divided by the rate of dissipation power to 1/4. And tau is equal to the kinematic viscosity divided by the dissipation square root of this ratio. So these are two very important numbers. And these are two very important numbers also when you are doing, for example, numerical simulations, okay? Because you need to understand where you put your meshes, how big is the size of the meshes, linked to the turbulence, let's say, length scales and time scales. So this is very important as a kind of reference dimension for the time and the length. One can say, nice, but this is not solving anything because then the kinematic viscosity is pretty well known. So we can know the dynamic viscosity and density. We have an idea of the kinematic viscosity. But what is happening with epsilon? Epsilon is, again, the rate of dissipation. Well, we need to go to the shear stresses. Well, yeah, remember that was already complex, and then when we have a complex system is becoming very complex. Well, I don't know. But again, we can say, okay, yes, you're right, it's very complex, but there are, let's say, again, simplification, saying that, well, lambda divided by a length is in fact proportional to the number of Reynolds that we saw before, power to minus 0.75, so 3/4. And in terms of time, we can say that the velocity, the mean velocity of the flow multiplied by the turbulence time scale, divided by this kind of length, is in fact proportional to the Reynolds, the square root of 1 over the square root of Reynolds, sorry. So, okay. This is not too bad, but okay, still very complex, but I'm not entering in this field. I don't have time. So, we need to determine the heat transfer coefficient in the boundary layer. So, it's possible to have estimation of what is happening using the Nusselt number. The Nusselt is H, this convection coefficient, multiplied by the characteristic length divided by the thermal conductivity of the fluid. Okay? And since we saw that it's possible to define average values for the H, then this means that we have average values for the Nusselt. Okay? And the Nusselt is a function, and here we can write this in terms of the Buckingham, the pi theorem, so the Buckingham theorem. We can say that the Nusselt, in fact, is a function of Reynolds and Prandtl. Reynolds we saw. Prandtl is nothing else than the kinematic viscosity divided by the thermal diffusivity. So you can understand that Prandtl is already linked to the thickness of the viscous boundary layer, and alpha is related to the thickness of the thermal boundary layer. Again, without demonstration, very sorry for that, but we need to continue. So, this is what we have at the end. We have different dimensionless numbers, and this is simplifying the approach. So, even now, as an editor of a journal, I'm receiving papers trying to establish how much is the H for different conditions. Can be in spray cooling, can be maybe not in obvious condition, but in many conditions with the two-phase flows, for example. So we have bubbles that are going inside the system, we have bubbly flow, what is happening in terms of H, how much is the H in this condition. We have, let's say, evaporation, what is the H when we have an evaporating fluid, and so on and so on. So at the end, let's say what is important now is to consider the complexity of the process, which is in fact, you saw, very complex, inside the number that we can use, let's say, because the physics, we know plus minus the physics, no? But we need a number to be able to have, let's say, a solution for our applications, okay? So this is just what we are doing. And we have here some supplementary material. Okay, I don't have time to do that because it's just 10 and that was really o'clock. More precise than that is not possible. 10 is my last slide for this first hour. So now we are going to have 10 minutes of break, I think. I don't see the guy. Is outside already. Okay, good. Okay. And then let's come back at 10 past 10, and we are starting with the multi-phase flow. And we have, in fact, 2 hours. I call 1 and 2, but at the end, in fact, is a unique lesson of 2 hours about multi-phase flows. Thank you.